So anyway, I think it's very appropriate that now when we celebrate 100th year anniversary of general relativity, we can think about how can we use this theory, not to test, but really to build something using general relativity. And this is what I will be talking about. So the talk here is essentially how to make a direct multipixel imaging of an Exo-Earth with solar gravitational lens mission. And that's the very idea of using the gravity as a lens was essentially proposed by Einstein himself, as Avi pointed. So this is the paper he wrote in 1911, and you see a first sort of drawing of the lens, and he computed the lens, and he computed the angles and all the features of that lens, and he actually concluded it's highly unlikely that the lens and Earth will have will coincide. So he put this idea kind of on the back burner, and then in 1913, actually, he decided to went a little bit further. He wrote a letter to Hale, and in that letter, he was asking, do we really need the sun to make a conjunction experiment to see if starlight is being deflected? And so this is the letter. Notice the angle was still 0.87 arcseconds. It's not 1.75 as we know it. So it was still Newtonian arguments and early versions of equivalence principles that led into this derivation. And so Hale reluctantly said, yeah, we should use the sun, but he was not really eager to jump on this idea and sort of to verify it. And remember, it was 1913. The first team that decided to actually test this idea was a German team led by astronomer Erwin Finlay-Friedrich. And he was able to mount an expedition, and he went to observe a possible deflection of light at that time. And he went to do this in Russia because eclipse in 1914 happened on August 21st of that year. And of course, we know that only a few weeks earlier, the First World War started. So nothing came out of that expedition. And so, but during this time, 3 years later, Einstein essentially knew exactly what should be the deflection of light. When he published the general theory of relativity, he knew that light will be deflected twice the Newtonian level. And so we know, as Avi pointed out, that Eddington actually did the experiment using solar conjunction in 1919. But what was interesting, at that time, there were 3 possible outcomes for the light deflection. Gravity will not affect light propagation, so deflection would be 0. Or Newtonian arguments, or Einstein's arguments that would be twice the Newtonian level. And so at that time, it was a wonderful time to conduct fundamental physics experiments because you have 3 possible outcomes. Only now we test 0, but previously it was the 3 very distinct results. And you see here, this is the telegram from Campbell. And Campbell, from Lick Observatory, he is actually saying that the confirmation that Einstein's deflection angle was actually observed. And so we see the 2 people, Einstein and Eddington, sitting here in Cambridge in 1930s. So this was the beginning. By now, we know that deflection is pretty much everywhere. So we build telescopes, we build observatories that would use microlensing, weak microlensing, strong microlensing to study universe. So this is out there. So it is well tested, and it's wonderful. For me, my laboratory is rather big. I'm living in the solar system. This is my laboratory, because at JPL, we fly spacecraft everywhere. We use data to essentially test Einstein's general theory of relativity. And we've done it really well. In the last 40 years, I just show a little history here. So we flew a number of spacecraft. We have planets. We use planets for microwave propagating beams, microwave beams to those planets, range to spacecraft, mariners, Viking pioneers, a number of laser engine expeditions like lunar laser engine, satellite laser engine, interplanetary laser engine soon. In this chart, I show just 2 parameters that actually were proposed by Eddington himself. So parameter beta would indicate the nonlinearity of gravitational superposition, and parameter gamma on the y-axis is the curvature of unit of space produced by unit mass. In general relativity, both of those parameters equal 1. So we've done some experiments. What is almost in 1976, ranging to Viking lander confirmed that the gamma would be deviating from unity from general relativity no more than 2 times 10 to the minus 3. Later on, So ranging to Mercury constrained that parameter space even further. So looking further, astrometric VLBI constrained it's much further. So now it's 10 to the minus 4. Lunar laser ranging even further confirming that possible deviation from general relativity. And of course, Cassini experiment flying to Saturn, we were able to confirm that Einstein's prediction was very correct at the level of roughly 10 to the minus 5. So now we know general relativity works in the solar system everywhere we try to do those tests. Quite a few experiments were conducted, Gravity Probe A, Gravity Probe B, built at Stanford University, of course. And of course, recent confirmation came from LIGO experiments. So general relativity works everywhere. It's time to consider that GR may be used as applied discipline, because now we cannot actually fly spacecraft without accounting for general relativity. What we do in astrometric observations, we have to account for GR. Light coming perpendicular to ecliptic is being deflected by solar gravity by 8 milliarc seconds. Remember Gaia? We're talking about microarc second. We have to account for Sun and Jupiter all the time when we look in the sky. So general relativity is there. But now it's time to really consider what can we do with it. And the very idea of using the Sun as a gravitational lens was born here in Stanford University. Von Eshelman, he was the radio science team PI on the Voyager 1 experiment. Essentially, he published a paper saying, look, we have to use the Sun as gravitational lens. So this is a paper published in 1979, suggesting that for communication purposes, the Sun is perfect. For interstellar communication, it's wonderful. And essentially, you assume that one pixel detector is somewhere behind the Sun, and the distance, he computed the magnification, and that was wonderful beginning of the whole sort of star, astro construction idea of using the Sun actually as a lens was born in a practical sense by von Eshelman. And we know that a number of papers were published, and Claudio Macon is here. He will be discussing the communication idea and significant work that was put by Claudio in this effort. And I think whatever I will be talking after this slide, it's Lou Friedman's fault, because Lou is actually was a great motivator to actually look at the lens, because it actually has a lot of potential. And I will be discussing this potential with you here. I stole a slide from Lou's presentation. So this is the slide that we come up with during the recent KISS study, Keck Institute for Space Studies at Caltech. And so as you go from the solar system, guess where? Alpha Centauri, right? And so on the way to Alpha Centauri, there are plenty of interesting targets. And you see Voyagers are here. Voyager just crossed the boundary of the solar system. As you go beyond that boundary, there is nothing. You have to be in space. You coast through a long time, and unless you're shot by the laser beams and you go there in 4 years. So, but crossing that boundary, this is a wonderful place here where I'd like us to go, which is the solar gravitational lens. It's exactly at 547 AU. It's begin rays which are grazing the Sun. The actual will be focused at 547 astronomical units. This is the geometry for the lens. If I assume that the plane wave impacting the Sun, and the rays just grazing the Sun will be focusing at 550 astronomical units. And you see the deflection of light, the angle of deflection is inversely proportional to the impact parameter. The larger the impact parameter, the less the deflection. Therefore, the lens is astigmatic. And we will use that feature in looking how that can be used. And another feature here is you see the focal length essentially is proportional to the square of the ratio impact parameter to the solar mass, to the solar radius. So it's actually, it's quadratic to this ratio, which is the larger the impact parameter, the further you have to go to actually benefit from the deflection. So those features we will use in the discussion further. So, but nevertheless, I'd like to emphasize a couple things. So for imaging purposes, this is just a cartoon. You see the object field somewhere on the significant distance. You see the Einstein ring around the Sun, and the image plane, you see that lens works actually. So you see that the two points on the surface spatially separated on the object will be spatially separated on the lens. So you will be able to resolve. And how well, we'll discuss it in a few charts down the road. So the two lenses, optical lens on the bottom, you see it right there, and essentially the gravitational lens is here. They're astigmatic. So there is no focal point. Essentially, it's a focal line. because it begins only at 547 astronomical units and goes all the way much further. If you take sort of geometric optical approximation, you get infinite gain. But if you take wave optical approximation, which we've done recently, so now we have complete wave optical treatment of the lens. We know how things are actually done at this range, and some of those important features I will discuss in a few charts. So here, what we have behind the lens, there are three regions which I'd like us to focus. Basically, if I go back to a chart here, so on the chart, on the bottom of this chart, you see that there is a shadow right behind the sun. Then there is geometric optics region where you have only sort of the rays just passing by the sun will be deflected, and so there is no really image. And the image will be done in a range where the interference occurring. It's just behind the lens. And so this is the most interesting region for us. We'll be talking about this region a lot during this few minutes down the road. So if I go back to this chart, so once we reach that focal distance, and so you see three different regions, and I will be focusing on the region which is just near the optical axis. This is the beam of extreme intensity. When I'm talking about extreme intensity, I'm using this expression for the magnification, for the gain. You see, in front of that expression, you see the ratio of 4 pi times the Schwarzschild radius divided by the wavelength of radiation. We know that 3 kilometers is a scale for the Schwarzschild radius of the sun, and lambda, if you take in 10 to the minus 6, if you're talking about the optical radiation, you get this factor is 10 to the 11th. So the gain is significant. We are there, it's a significant gain for optical radiation, it's 10 to the 11th. And so here, what is interesting is that the gain actually oscillates. There is a fast oscillation, not only as you go in the image plane from the optical axis. It oscillates with a period of roughly 10 to 15 meters. So we're talking about, we reached 550 AU. It's way out there, but the oscillations are with a very short period. So with the emitter telescope, we will be averaging a lot of radiation here. We'll be averaging a lot of those area lobes there. So, but because of it's a very highly oscillating region, and also it will be there is an interesting behavior for a fixed row, which is a point on the image plane. If you go further away from the lens, the gain is increasing. So it looks a lot similar to that tsunami. I will show a couple of slides which are very familiar here on the ground. But here you see sort of the gain for different types of radiation. For 1 millimeter, for 0.1 millimeter, you see for 1 millimeter the gain is 80 dB, and for 0.1 millimeter is 90 dB, so which is quite significant. You see the scale of oscillations are larger for the for longer wavelength. So going further, I mentioned that tsunami. For example, we are very familiar if event is happening, earthquake happening in the ocean, and you see you have a mountain on the bottom of the ocean. So it's actually this mountain actually works as a lens. It's also a astigmatic lens, and you see how it works here. So it actually forming a folded caustic behind the lens, and actually provide a significant amplification. You see here those sort of the on the right picture here. You see sort of the wave fronts of the same time. You see that the plane wave comes to the lens, and then once it passes by the lens, the wave fronts are going to be bent, and then when they propagate, they will actually combine and form the folded caustic. And this is the nature of the physics that we're dealing with here. Again, the same lens. The same tsunami, and you see how gain is oscillating here. It's oscillating as we go away on the image plane and as we propagate further. So this is the same feature, pretty much similar feature that we have in wave optics treatment of that lens, which we are discussing here. But let's put numbers together. So when I am, if we fly a 1 meter spacecraft, and if 1 meter spacecraft will be situated somewhere roughly 550 astronomical units away from the lens, having the fact that there is a gain 10 to the 11th in the optical axis, so this 1 meter telescope is equivalent to 80 kilometers aperture at 1 AU. 1 meter there, 80 kilometers here. And so the gain is significant. So the features of that lens are the following. So we have a very significant brightness increase, a factor 10 to the 11th. There is also a very sharp angular resolution. We're talking about 0.5 nanoarc seconds. And so because of that angular resolution, which is just native to this lens, we are able to think about direct multipixel imaging, because a planet at an Earth-like planet 30 parsec away, with this type of resolution, we should be able to see a 10 by 10 kilometers feature on the surface of that planet. And so this is why the idea has some merits to at least to study further. So we need to understand if it actually works through instrumental. As we were saying at the beginning, physics is there, it's just engineering now. So moving on, so what is interesting with this resolving power, the contamination from parent star is totally relevant because we resolve planet itself. The star parent star is focusing many AUs out, so it's not really an issue here. So the entire Exo-Earth will be within 10 by 10 kilometers spot around the optical axis. So we have to sample that 10 by 10 kilometers. I like this as a CCD with 1,000 by 1,000 pixels. And so we have to sample pixel by pixel to get the whole image. And so that this CCD is 10 by 10 kilometers in the case of Exo-Earth. And so what also is interesting, again, the spatial period for oscillations, this is very interesting. Okay, now we have this here, and the challenge is, of course, can we use conventional techniques? If I think about the telescope, if I build an 80-kilometer telescope using, let's say, if I even try to fly it, so if I use a 1 micron thick film, and if I build it in space, it will weigh 10 to the 12 kilograms. It will be a significant solar sail. It will be, this telescope will be removed from the solar system by solar radiation pressure within less than a year. So it's not practical. If I'm talking about interferometer, to talk about the resolving power of 0.5 nanoarc seconds, what I need to do, I have to have interferometer which will have baselines of roughly 6 times the diameters of the Earth. So if I have two 10-meter telescopes forming the interferometer, integration time to beat down the SODI, it will take us what, roughly 400 million years to get information, to get a signal-to-noise ratio 10. So interferometer, but now it's not imaging yet, we just resolving power. If you want to do image for 1,000 by 1,000 pixels, you need to have million baselines. And so million baselines, you either rotate this interferometer or you to fill in the UV plane, or you have to build million baselines. And of course, the integration time sort of decreases with the number of baselines. But still, what we're talking about, if we have roughly 2 of these telescopes, 10-meter telescopes will be available. We basically need to multiply by 1,000,000 times to get a very significant time to get the signal. So interferometer, what I'm saying here, is really impractical as well. So to have comparable resolving power and magnification with techniques that we know today are impossible. I mean, it's beyond the engineering issue. Let's put it this way. And so moving on, the solar radiation, the solar gravity lens essentially is very challenging but viable alternative to what we have today. Of course, you will say when you buy a telescope, what actually many will say, don't look at the sun with this machine. But we will going to look exactly at the sun. So that's the challenge here. And so looking exactly at the sun, the point is we know the sun is very violent source. We don't want to look at this, but in this case, we have to look at the sun. We have to block the sun. And there are 2 effects that come against us. First one is, of course, the solar corona. Solar corona, when light goes through the solar corona, it's actually been affected. There is reflectivity within the solar corona. But it's not that bad for optical wavelength, because when you look at the reflectivity of solar corona, so deflection angle will be affected by refractivity in the solar corona and the gravitational. So these 2 effects work against each other, because for an observer at the focus of the length, the solar plasma will work as moving the objects close to the sun. And for a gravity will work moving apparent motion outside the sun. So it's actually the 2 effects have opposite signs. When we looked at the models using Cassini model which were tested with Cassini spacecraft, Cassini corona model, the idea is that for for smaller frequencies, for small observing frequencies, essentially our observing distance have to be pushed way out there, beyond 550 AU. If we observe in the higher frequencies, it actually becomes kind of irrelevant. So for terahertz, the observing range starts not from 550, but roughly at 600 AU. And for 100 terahertz, we're talking about optical wavelength, it's pretty much irrelevant. But solar brightness is important. So, so this is second effect. And solar brightness is significant, and taking actually all the information about solar brightness, it's still very interesting. So what we have here, so to image this an object, an Earth with sort of within the image plane, the Earth occupies 10 by 10 kilometer spot. We have 1,000 by 1,000 pixels, and to form an image, we have to be able to go pixel by pixel, because each pixel will represent different impact parameters, and will actually surface areas which will be adjacent to each other on the surface of the Exo-Earth will be imaged to 2 pixels which are adjacent to each other in the image plane. There will be, of course, blurring, because the lens being astigmatic from one spatial pixel, there will be light leaking inside, so there will be significant blurring, and roughly we estimate maybe up to 25% of the light we'll get in one pixel will come from adjacent pixels. So, but still, it's the noise we can deal with. So essentially, to build this 1,000 by 1,000 pixel image, we have to navigate. We have to move inside the image plane. Instrumental design. We will actually. I think it's just stopped on me. So yeah, Microsoft encountered a problem, and Microsoft PowerPoint. So I guess I'm unfortunately. Can we restart it, or it asked me to send a message to Microsoft? As we begin. So essentially, we need to sample this image, and the sampling this image can be done. It's either flying a swarm of spacecraft, or you can fly two tethered spacecraft. As they move in the image plane, you sample that radiation one by one, pixel by pixel, and that essentially is very doable thing. So we do the image. We have to use a coronagraph, and the coronographic techniques. We understand that this is a rather very important development recently. We heard about this development through the last 2 days, and essentially flying a coronagraph, which is very simple 10 to the minus 6 contrast ratio. So we can be we will be able to get a very good signal here. So when we talk about putting the numbers together, when we talk about not the Exo-Earth at 30 parsec away will be an object of roughly 32.5 magnitude. So, but we're talking about a thousandth of that object. So essentially, it's 47th magnitude object, which is just a spot on the surface of that planet. What we have here is that the solar gain gives you roughly 27 magnitude improvement here, and essentially taking into account that there will be Zodi background. So we have to look at basically an object of 90th magnitude on 15th magnitude background. And so essentially it will take us roughly 2,500 seconds to integrate to get the signal. So we've done geometric ray tracing, we know how it works. We've done some convolution and deconvolution just using the black hole as a starting image. We put some photon properties, and actually we were able to deconvolve, so imaging properties are really good. We need to know a lot of information about a priori information about the target, and all the techniques that were discussed earlier are very relevant. So this is how we'll fly in the image plane, tethered spacecraft, and essentially moving on the planet. The orbital motion and also the rotation helps us to actually decouple lots of information, lots of features of that planet, and we will be able to get that. To do this right, we need to do a study, of course. So because we are not saying that we know everything, and this is the sort of the chart that summarizes the study we would like to do, focusing on the features and studying the feasibility of this concept for actually to fly a mission like this for direct imaging of exoplanets, maybe in the near future. Thank you very much.